Dear students, now we shall discuss about the chemical properties of alcohols. We know that alcohols are amphoteric substances. Alcohols are amphoteric in nature. Alcohols are amphoteric in nature. What is this amphoteric nature? These substances are able to act as acids as well as bases. These are able to act as acids as well as bases. Okay. Let us see the evidences for the behavior of alcohols as acids. Okay. Let's take the alcohol. Okay. This is the general representation of the alcohol where the oxygen atom is carrying the lone pair of electrons, okay, and oxygen is the more electronegative element, okay, and hydrogen is less electronegative element, and due to the high electronegativity of oxygen it will pull the bonding electrons towards itself and it becomes slightly rich in electron density and gains the delta minus charge, okay, and hydrogen will gain the delta plus charge. Means the alcohols are polar in nature. Alcohols are polar in nature. Okay. Due to this electronegativity differences between the oxygen and the hydrogen, this bond becomes weak. This OH bond becomes weak, and it break into this way. Okay, and it breaks into this way. Here you can see this alcohol is acting as a proton donor. Okay, alcohol is acting as a proton donor. Means accordingly the Bronsted-Lowry concept, acids are proton donors. Acids are proton donors. Acids are proton donors. Yes, here the alcohol, due to electronegativity differences between the oxygen and the hydrogen, is having polarity and donates the H plus ion. And leaving this RO minus, it is called as alkoxide ion. It is a base. Keep in mind that it is a base. Okay. Now in this reaction you have seen that alcohols as proton donors and Bronsted-Lowry acids. Okay. Let us consider some other reaction. For example, ROH. Here also the oxygen having lone pair of electrons when it is subjected for an acid. Usually acids are represented by the H plus ion because acids nothing but proton donors. Okay, here H plus ion is called as a proton. Okay, yes, here due to the presence of lone pair of electrons on the oxygen atom, okay, it acts as a nucleophile and H plus ion is electron deficient and it is a electrophile. Okay, yes, these lone pair of electrons on the oxygen will take up this H plus ion and forms the structure like this. In this, you can see that initially there were two lone pair of electrons on the oxygen atom. Now it has lost one lone pair of electron and takes the positive charge Okay, and it is unstable also. See, this is an alcohol. Okay. This is the protonated alcohol. Protonated alcohol means alcohol to which a proton is added. Okay. And in this reaction, you can see that the alcohols as proton acceptors. Hence, same accordingly the Bronsted-Lowry concept, bases are proton acceptors. Okay, according to Bronsted-Lowry concept, the bases are, okay, proton acceptors. Okay, from these two reactions, we can visualize that alcohols are exhibiting the acidic character as well as a basic character, hence alcohols are said to be amphoteric substances. Okay, and keep in mind that when alcohols acts as a proton donors or acids, it is due to the presence of polarity. It is due to the presence of polarity. Okay, when the alcohols acts as a basis, when there are lone pair of electrons on this oxygen and acts as a nucleophiles. Okay, yes. After this, we shall discuss about some chemical reactions involving cleavage of this OH bond and cleavage of this CO bond. Okay, firstly we shall consider chemical reactions involving cleavage of OH bond. Okay, chemical reactions involving cleavage of OH bond. Okay, we shall consider the chemical reactions involving cleavage of OH bond. Okay, yes, in this firstly we shall take up the reaction of alcohols with metals. Okay, reaction of alcohols with metals. Reaction of alcohols with metals, and this proves the acidic character of alcohols. Okay, yes, for example, when an alcohol, for example you may take the CH3OH, that is a methanol. When this treated with a active metal, for example sodium, it forms CH3ONa. This is called as sodium methoxide. Okay, what is coming out? The hydrogen is coming out, like alcohol is acting as a proton donor, means H plus, or in the form of a gas it is coming out. We can write that as a H2 gas here. Okay, so based on this reaction it is releasing the hydrogen gas, hence it proves the acidic character of the alcohol. Similarly, let's consider some other active metals, for example aluminium. See here, what is the difference between the sodium and aluminium? Both are active metals, but sodium is a monovalent. It reacts with 1 mole of the CH3OH, while aluminium is a trivalent. For that you need to take 3 moles of alcohols. Here we shall take up the tertiary butanol. Okay, any alcohol you may take. I am going to take the tertiary butanol to show all alcohols, means primary, secondary or tertiary. These are all exhibiting the acidic properties. Okay, yes, we have to take the 3 moles of alcohols. For example, it is butanol, that is tertiary butanol. Okay, when this tertiary butanol is treated with the aluminium, okay, it forms the tertiary butyl oxide aluminium or aluminium tertiary butoxide. Okay, for example, here after reaction you get this compound CH3O. You know that already I told you aluminium is a trivalent. Like this. Okay, here there is a formation of this compound. Okay, with the release of hydrogens. How many hydrogens are coming out? 3 hydrogens. Okay, and the hydrogens are represented in the form of a molecule. Okay, for that I am going to write this as 3/2H2 gas. Okay, and it remains 3 hydrogen only. Okay, this 1/2 and this 2 gets cancelled. It remains only 3 hydrogens, but we have to write the release of hydrogen always in the molecular form. Okay, yes, these two reactions are evidences for the acidic character of the alcohols. Okay. Now we shall discuss about the factors affecting acidity of alcohols, and keep in mind that the acidity of alcohol is majorly because of polarity of OH bond. If any group is going to affect the polarity of the OH bond, definitely it affects the acidity of the alcohol. Here we shall consider two groups. Okay, one is electron donating group and another one is electron withdrawing group, and see how these are going to affect the acidity of the alcohol. For example, let us consider the electron donating groups. Here usually the alkyl groups are electron donating groups. As the number of electron donating groups increases, as the number of electron donating groups increases, it decreases the polarity. It decreases the polarity. When polarity is decreased, definitely acidity also will decrease. Okay, so polarity and acidity decreases. Polarity and acidity decreases. Okay, here when you go on adding the electron donating group onto the carbon, okay, it decreases the polarity. Let's see how. Okay, for example, you take the isomers of the alcohols. For example, primary butanol CH3, CH2, 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 OH. It is a primary butanol. Okay. And take the secondary butanol CH3, CH2, CH, OH, CH3, and take the tertiary butanol, for example, CH3, 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 OH. Okay, these are all isomers. These are all isomers. Okay, yes, isomers of butanol. Okay, yes. Here you can see that this is the carbon holding OH group and having the propyl alkyl group. This acts as a one alkyl group, means it acts as a one alkyl group. Okay. Come to this. This is the carbon containing the functional group OH, and here on this side you have one ethyl group, and on this side you have another methyl group. Means it contains two alkyl groups. Okay. Come to this. This is the OH containing carbon and it has three alkyl groups. Okay. Here, what you are observing? You are observing the increasing number of alkyl groups on the functional group containing carbon. What happens? Alkyl groups are electron donating. Alkyl groups are electron donating. Okay. Now, if you consider this molecule, here you have OH bond. These are donating electrons due to the inductive effect. Okay, these are donating electrons to this carbon. Okay, and slightly the electron density is more on this oxygen, and it forms no chance to pull electrons from the hydrogen. Okay, in this case there is only one alkyl group, and here the oxygen felt no much pulling of electrons from the hydrogen. Okay, because the electron density on this oxygen is somewhat more. Okay, come to this molecule. Here you can see the OH bond. Okay, here there are two electron donating groups to this carbon and subsequently to this oxygen. Okay, here there is still more electron density on this oxygen. It feels not to pull electrons from the hydrogen again. Okay, come to this group. Here there are three electron donating groups. The density, electron density on this oxygen is very high, and it felt no chance to pull electrons from this OH bond. Okay, now in this case electron density is very high, so polarity is very less. Polarity is very less. polarity is very less. Okay. Here we have to consider polarity of OH bond. Polarity of OH bond is very less. Okay. Come to this molecule. Polarity between OH, there is a polarity of OH bond is less. Okay. Polarity of OH bond is less. Okay, is less. Okay. And come to this molecule. Here you can see that polarity of OH bond is high. Is high. Among these three, that is primary, secondary, and tertiary alcohols, where there is a high polarity in this molecule, hence this is more acidic. Okay, and this is more acidic. So this all works very well in the aqueous medium. This works very well in the aqueous medium. But when it comes to the gaseous phase, the order of acidity is different. Okay, so here I am going to write the order of acidity. Order of acidity in aqueous medium. In aqueous medium is like this. In aqueous medium is like this. The water is more acidic than the alcohols. Okay. Now, in the alcohols, the primary alcohol is more acidic, followed by the secondary alcohol. Okay, and followed by the tertiary alcohol, Okay. So the conclusion is that as we increase the number of electron donating groups on the alcohol, its polarity decreases, thereby decreases the acidity of the alcohol. Okay, and this is the correct order for acidity of alcohol. This works very well in the aqueous medium, but in gaseous phase it is little bit different. Okay. Yes, here we shall consider the acidity of alcohols versus water. Okay, let's consider the acidity of water versus alcohol. I told you that water is more acidic than the alcohol. How? Let us consider the reaction. Ru minus. Assume that we have alkoxide ion. I already told that it has a base. Okay. When it is treated with water, okay, that is HOH. Okay. Now what happens? H2O donates a proton to this alcohol. It becomes ROH. This is an alcohol. Okay. It was a base on the left hand side of the reaction. Now it is the conjugate acid of the base. In the right hand side. Okay. Now the H2O becomes OH minus. Okay. H2O becomes OH minus. It is a conjugate base. See, when you look at this reaction, which one is acting as a proton donor? The H2O. It is acting as a proton donor. Hence, it is considered as an acid. Okay. And it is a strong base. Usually, when you compare the basicity of hydroxyl ion OH minus and alkoxide ion RO minus, the basicity of this alkoxide ion is higher. Okay. Yes, in this reaction, you can see that the water is highly acidic when compared to the alcohols. Okay. Order of acidity. The water is more acidic than the alcohol. Okay. Yes. Now we shall discuss about the effect of electron withdrawing group on the acidity of alcohol. Okay. As the number of electron withdrawing groups increases, polarity and acidity increases. acidity increases. Okay. Okay, let's say some of the compounds. Okay, you have CH3, CH, NO2. Okay, and here it is having OH, and CH3, CH2, OH. Okay, here it is all about the polarity of OH bond. Okay, if you take this as OH and take this as OH here. Okay, here we have electron withdrawing group. Okay, means it will pull the electrons from this carbon. It will pull the electrons from this carbon. Now this carbon is electron deficient, so that it will try to pull the electrons from this. Okay, electrons from this. Now it is making a less electron density on this oxygen, hence it has to gain electrons from this OH bonds again. Now it is increasing the polarity of this OH bond. Okay, therefore acidity also increases. Come to this molecule. Here we have lone pair of electrons on the oxygen. Okay, and the alkyl group is electron donating group. It is donating the electrons to the oxygen, and it is increasing the electron density on the oxygen. It feels no need to pull the electrons from the hydrogen. Hence, its polarity is less. Its polarity is less. Okay. And here there is a high polarity. There is a high polarity. Okay. In OH bond. Therefore, it has more acidic nature. Okay. So, the conclusion is that when you take or increase the number of electron withdrawing groups on the molecule, polarity and acidity increases. Polarity and acidity increases. It is all about the factors affecting. What are the factors here? Electron donating groups and electron withdrawing groups. And these are affecting the polarity of the alcohols, thereby affecting the acidity of alcohols. Now we shall discuss about the esterification. Here also you can see the cleavage of OH bond. Here also you can see the cleavage of OH bond. Okay. Esterification is nothing but formation of esters. When alcohols are treated with the carboxylic acids, in the presence of an acid gives the esters. Okay, let us consider esterification by using the alcohols and carboxylic acids, alcohols and acid anhydrides, alcohols and acid chlorides. Let's go one by one. Okay, so when alcohols are treated with carboxylic acids, alcohols treated with carboxylic acids, treated with carboxylic acids, with carboxylic acids. In presence of the acid, okay, gives the ester. Okay, let's see the reaction for this. Take any alcohol here. Let's say it has R-OH. Here R- is an alkyl group. You know, alcohols are treated with carboxylic acids. Let's take RC double bond OH. I will write this like this. Okay. RCOOH. It is nothing but a carboxylic acid. It is nothing but a carboxylic acid. Okay. Yes. This treatment, that is treating alcohol with the carboxylic acid, is done in the presence of an acid. In the presence of an acid, for example H2SO4 or HCl we use. It acts as a dehydrating agent as well as a catalyst. Okay. Now here you can see the cleavage of OH bond. Here you can see the cleavage of OH bond in alcohol and cleavage of CO bond in carboxylic acid. Okay. So what we are dealing with? We are dealing with the cleavage of the OH bonds. Okay, here in alcohol you can see the cleavage of OH bond, and it results in the acidic nature of the alcohol also. Okay, yes. What is coming out? H2O is coming out as a byproduct, and here you are going to see that RCO OR dash as the product. RCO double bond OR dash as the product. This is called as an ester. This is called as an ester. Okay, the byproduct is H2O. Here we can see that double-headed arrow mark. It means that it is a reversible reaction. Means when you treat the alcohol and carboxylic acid in the presence of an acid, it gives ester and H2O. If you leave this reaction mixture as it is, after some time H2O start reacting with the ester and gives back the carboxylic acid and alcohol. So for this type of reaction we call as a reversible reaction. It can take place forward and backward. Okay. So what we have to do, we have to remove the H2O as soon as it forms. As soon as it forms. Okay. Yes. Let's take a suitable example. For example, I am going to take the CH3OH. CH3OH, it is a methanol. It is a methanol. Okay. It is treated with the acetic acid, for example. Okay. Take the acetic acid, that is CH3COOH. Okay. We also call this as ethanoic acid. We also call this as ethanoic acid. You know that ethanoic acid is a IUPAC. Okay. Yes. This reaction takes place in the presence of an acid. Okay. And here you can see the cleavage of OH bond. Okay. And in this case we can see the cleavage of CO bond. Yes. Now the product is CH3 C double bond O CH3. This is called as methyl. This is the substituent. Okay. Methyl and 2 carbon atoms. Word root is ethanoate. So it is called as a methyl ethanoate as the compound. This is an ester. Okay. And the byproduct is H2O, and the byproduct is H2O. Okay. So what is an esterification process? The alcohols treated with the carboxylic acids in the presence of an acid gives the esters. This process is called as esterification. Okay. Here we can also see the esterification by treating the alcohols, with acid anhydrides. Okay, with acid anhydrides. Okay. Yes, alcohols treated with acid anhydride. Let's take the general reaction equation. R dash OH. Okay, this is an alcohol, and take the acid anhydride, that is RCO twice O. This is called as acid anhydride. Okay, actually these are prepared from the dehydration of the carboxylic acids. Okay, that is why these are called as acid anhydride. Anhydride means loss of water. Acid here it refers to, these are manufactured from the carboxylic acids. Okay, when these two are treated in the presence of an acid, okay, what happens? Cleavage of OH bond takes place. Okay, and here one of the RCO combines with OR dash. Okay, then you get RC double bond OR dash. This is an ester. And what is the byproduct? One more RCO is present, along with the O is present, RCOO, H is coming out. So you can see that RCOOH. What is this? Carboxylic acid. This is carboxylic acid. Okay. From these two methods, you are getting the esters. Here the reactants are different and the byproducts are different. Okay. Yes. Let's consider the suitable example. When you may take the same alcohols, that is CH3OH, when the methanol is treated with the acetic anhydride, What is this? This is the methanol treated with acetic anhydride. Okay. In the presence of an acid, okay, what happens? This bond is breaking. Okay. Now CH3CO is joining with this OCH3. Okay, you will get CH3 C double bond O OCH3. This is called as methyl ethanoate as in this case. Okay, methyl ethanoate. Methyl ethanoate. Okay, it is an ester. Okay, what is the byproduct? What is left here? CH3COO along with this H. So you will get that acetic acid is the byproduct. This is called as acetic acid or ethanoic acid Okay, you must remember the names of the compounds. Okay, sometimes the compounds will have both the common name and IUPAC name, that you have to remember. Okay, here you can see the preparation of esters from alcohols using carboxylic acids and using acid anhydrides. Now we shall see the preparation of esters using alcohols and acid chlorides. Now let us consider the esterification reaction between the alcohols and acid chlorides. This reaction takes place in the presence of a base. We use pyridine as a base here. Okay, let's see the general reaction equation. We have taken the alcohol R-OH, okay, and take the RCOCl, or we can reverse this representation Cl C double bond O R to understand it easily. Okay, this reaction takes place in the presence of pyridine. Pyridine is a base. Okay, why we require base? In previous two reactions we required the acid. Okay, here we are requiring the base. Okay, why? Let's see. When this alcohol is treated with the acid chloride, you can see the cleavage of OH bond in the alcohol and cleavage of this CCl bond in the acid chloride. What it forms? HCl. Okay, and it joins RCOOR dash. Okay, the product is RCOOR dash. This is an ester, and byproduct is HCl. See, HCl is an acid. To neutralize the acid formed, we are going to use a base. What happens if you don't use the base? The reverse reaction takes place. That is why whenever the HCl is formed as a byproduct, that will be neutralized with the base, that is pyridine. Okay, let's take suitable example here. Take the CH3OH, okay, and CH3COCl, but representation is like this: CH3COCl, to eliminate these two quickly. Okay, yes. So this is what? Acetyl chloride. This is acetyl chloride, and you know this as methanol. Okay, treat these two in the presence of a pyridine. It is a base. Okay, to neutralize the HCl formed. Okay, so the product is CH3COOCH3. Again, this is a methyl ethanoate. Okay, and the byproduct is HCl. Say in the previous two reactions, that is reaction of alcohols with the carboxylic acids and acid anhydrides, you used H2SO4 or HCl as a catalyst, and it also functions as a dehydrating agent. Okay, and here you are going to use the pyridine. Okay, that is the basic medium, to neutralize the HCl. Okay, this is all about the reactions involving cleavage of OH bond. Firstly, we have considered reaction with metals where it proves the acidity of alcohols, and here also we can see the acidity of alcohols, and this is in the esterification reaction. Okay.